Hello, welcome to everyone. I would like to explain moment of inertia in this video. Before that, I just introduce what is moment of inertia. We have learned two types of motion. One is linear motion or the translational motion, and the second one is rotational motion. In translation motion, the object is in a particular direction, right? If the body can move in a particular line, or it is in a particular space or in a particular place. We have learned two types of motion. One is linear motion or the translational motion, and the second one is rotational motion. In translation motion, the object is in a particular direction, right? If the body can move in a particular line, or it is in a particular space or in a particular plane. So that type of motion of the objects are known as translational motion. And what is rotational motion? Suppose the object is rotating in a particular axis, that type of motion is called rotational motion. So in the rotational motion, the object is moving with a particular axis. Okay. Now we are going to compare some important entities in both rotational and translational motion. Look at this table. The first entity is the displacement. In translational motion, we are using S, or the distance traveled by the object is called the displacement. The shortest path traveled by the object is displacement. We are using letter S to denote displacement in translational motion. Whereas in rotational motion, we are using theta. Theta is the angle subtended by the object in a translational motion, in a rotational motion, sorry. Similarly, in velocity, in translation motion, we are using V to denote the velocity of motion, where in rotational motion, we are using omega. And acceleration, for acceleration, we are using letter A, and here it is alpha. Alpha is equal to V square by R, and also the omega is equal to V by R. This implies that omega is equal to V equal to R omega. So this is a relation between V and omega. And for momentum, we are using P. We know momentum is a vector quantity. Both all acceleration, velocity, displacement are vector quantities. Similarly, the momentum is also a vector quantity. P, letter P is used. We know the momentum of an object is defined as the product of mass and its velocity. In rotational motion, we are using capital letter L to denote the angular momentum, and that is equal to R cross P. R is the distance between the point and the axis of rotation. But for mass, we are using M to denote mass in translation motion, whereas in rotation motion, we are using the letter inertia. That is the moment of inertia. Capital I is the letter used to denote moment of inertia in rotational motion. Okay, so in translation motion we are using mass, but in rotational motion we are using moment of inertia. But there is some difference between these two, because it is defined as mr square, that is mass into, suppose consider this type of object, and the mass, the different points denotes the different masses, and they are at their distance r1, r2, r3, etc. So the moment of inertia not only depends on the mass, but also depends on the distance between the axis and the point. Let me explain with a small thing. That is, suppose you consider this bottle. Okay, the bottle is full of water. Okay, so suppose I am rotating like this. Suppose I am rotating the bottle like this, so it will be easier for me. But suppose if you are using like this, so I have to do some more work. Understand? That means to rotate the object, the distance between, so this is the axis of rotation. Okay, this one is the axis of rotation, and this is a point. This is a point. This is from R1. So this is at a distance R from the center. Understand? So the distance between the point and the center plays an important role in moment of inertia. Okay, so this will be very easier because here the moment of inertia is less, and suppose I am rotating like this, that means the distance now increased, right? The distance is increased, r is increased, so r is also playing an important role in moment of inertia. See, when the r increases, the inertia increase is square. That is, r is proportional, I is proportional to r square. I is proportional to r square. So whenever, so if the distance increases from the axis, then the moment of inertia also increases. Okay, so what is moment of inertia? In mass, normally mass plays an important role in the motion of objects in translation motion, because mass is defined as the tendency of a body to resist the momentum in translation motion. Similarly, moment of inertia is an entity or is a tendency of the object to resist the angular momentum. Okay, angular momentum, it is defined as I is equal to mr square, where r is the distance between the center and the point of that mass. Okay, now we are going to derive the equation for moment of inertia. Look at that. The moment of inertia is not a constant one. That always depends on the distance, and also it is depends on the shape of the object. Okay, fine. Now we are going to derive the kinetic energy of the object which is in the angular rotation or angular momentum. Listen, suppose you consider this type of lamina, this type of irregular shape, okay, and this dotted line represents the axis of rotation. Now let us consider different masses, m1, m2, m3, m4, different masses are there at different positions, and they have different distance from the center of axis or axis of rotation. Okay, anyway, the total kinetic energy, we know the basic equation for kinetic energy, that is half mv square. That is in translation motion. Here we are going to substitute that v by omega. Let us see how it will be. Okay, the kinetic energy then, kinetic energy is equal to half m, instead of v square I wrote like r square omega square. Okay, we know the masses are at different positions. Okay, masses are at different positions. Let the mass of ith particle will be half m I r I square and omega square. Okay, so we are going to aggregate all the particles. So we are using the total kinetic energy will be equal to the summation of n is equal to 0 to, so here it is I, no? Okay, I is equal to 0 to 1, 0 to n. Suppose you consider there are n number of particles, then this is equal to m I, that is half m I r I square into omega square. Now we can write this equation as half omega square into summation of I equal to 0 to n m I r I square. Okay, so this part is equal to I. Therefore, k equal to half I omega square. Okay, so this is the equation for the kinetic energy in the case of angular rotation motion. Here I equal to the summation of I equal to capital I, the moment of inertia I equal to the summation of I equal to 0 to n m I r I square. Okay, in general we can write this equation as this one, that's all, mr square. Okay, you understand? Okay, now we are going to take an example. So in the case of circular objects like this type of objects, so this is circle. So suppose you take this point, so this is the center. Okay, this is the center of, or this is axis of rotation of the object is rotating like this. So this is the angle, this is the axis of rotation. Okay, this is the center, and suppose you consider this is the radius. Okay, radius of the object. Then what happened to the kinetic energy? Yes, we know that suppose the object, so suppose a particle is here, you take that distance as r1, here it is r2, here it is r3, and this one is r4, and so on. Different particles are there, so different radius, the different distance will be there between the axis and the point. So the kinetic energy is the sum of all the points, sum of kinetic energies of all the points. Okay, so this is the equation for that, and hence we can derive the equation for I is equal to, what is I equal to sigma, or summation I is equal to 0 to n m I r I square. Okay, so this is the equation for the moment of inertia. Okay, now we are going to take the object like this. So this is a circular ring, right? So here, so what will be the change in the equation? Suppose, so this is a final equation that we have, this is a final equation, right? This is a final equation. So what will be the change? So in this case, there is no different points, right? Only the distance is from the center is only r. Therefore, we can rewrite this equation as I equal to m r square, where m is the mass of this ring and r is the radius of this ring. This is one case. So in another case, you just think about a circular object like this. Circular object like this. So we are placing different objects here. This is m like this. So this is the entire object, and here we are placing a mass. That is m by 2. Here also we are placing a mass m by 2. M by 2. Suppose this is the length of the, so this is this length. This is the length, no? So this is the length of that object. Then this distance will be L by 2, and this distance will be L by 2. Okay, so here we are using, what we are doing is, so we are taking a rod having length L. We are placing two weights here and here, and we are just rotating this. Then we are going to find out what is its moment of inertia. Okay, so this is the diagram for this arrangement. And here, so how do you find out the moment of inertia of this object is m by 2 into L by 2 whole square, plus moment of inertia of this object will be m by 2 into, that is mass into distance square, no? So yeah, L by 2 whole square. So by doing this, we get m by 2 L square by 4 plus m by 2 L square by 4. Okay, so 1 by 4 can be, 1 by 2. 1 by 4 can be taken outside. 1 by 4 into 1 by 4, and L square by 4 can be taken outside. L square by 4 can be taken outside, and this is equal to m by 2 plus m by 2, that is m itself. Therefore, the equation becomes m L square by 4. So this is the equation of the rod which have the equal masses at the two ends of the object, and if it is in the rotation motion, then what will be its moment of inertia? The moment of inertia is equal to m L square by 4. So from these derivations, we concluded that the moment of inertia is not only depends on the mass, but also it depends on the axis or the distance of the object from its axis of rotation. Okay, So this is the moment of inertia, and also we learn that the moment of inertia is the tendency of the object to resist the angular momentum. So when if the moment of inertia is greater, then we need uh, more energy to rotate that object, to make the object to keep in a particular rotational motion. So this is a theory. And what is the difference between mass in the translation motion and mass in moment of inertia and rotation motion? That is, in translation motion, the mass is a constant one, but in rotation motion, the moment of inertia is not a constant, but it depends on the distance of the object or the distance of the point from the axis of rotation. So also the mass resists so similar case is here in translation motion. Mass resists the translation motion, right? Similarly, here in a moment of in rotation motion, the moment of inertia resists the what the rotational motion. Okay, then so the second one is yeah, so this is the first case. Okay, let us summarize. In translation motion, mass of a body resists its state of momentum, linear momentum. But in rotation motion, the moment of inertia resists the angular momentum. Okay. So one thing you have to remember is the rotation motion, I depends on. Okay. Hope you understand. Thank you.